Welcome to STAT200. This supplementary lecture concerns random variables. We've seen them before, but let's take a look at this material and dig in a little deeper. This covers Chapter 5 material, so let's get started. A random variable, what is it? Well, capital X, the symbol, is a discrete random variable. That's the kind we'll consider if, first of all, the values of x are discrete numbers. It has to be numeric because we want to do arithmetic with them. The second characteristic of a discrete random variable is for every possible value we assign a probability. We call it p of xi. And because this creates a probability function, we also have the requirement, of course, that the probabilities are all between 0 and 1, and they add up to 1. So for example, for a random variable taking values 1, 2, 3, 4, we could have a probability function as given here. The probability of getting a 1 is 0.4. The probability of getting a 2 is 0.3. The probability of getting a 3 is 0.2. And the probability of getting a 4 is 0.1. This qualifies as a random variable now because the probability of each value is a number between 0 and 1, representing a valid probability, and they add up to 1. 0.4 plus 0.3 is 0.7, plus 0.2 is 0.9, and plus 0.1 gives me 1. So the probabilities add up to 1, so this is a valid random variable. A better example that's more consistent with what we've been learning, suppose I toss a fair coin 3 times. Then the sample space of outcomes is not numeric, it's these possible outcomes: heads, 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 tails, heads, tails, heads, etc. There's 8 possible different outcomes that make up my sample space, and they all have equal probability 1/8. Why is that so? Well, because the probability of getting a heads is the same as the probability of getting tails, it's 0.5, and because these experiments are, the repeated trials are independent, we multiply. So 1/2 times 1/2 times 1/2 is 1/8 in every one of these cases. So now I can turn this probability space into a random variable by, for example, I can create the random variable x as the number of heads in 3 coin tosses. That's a numeric value. Then it should be clear the probability of getting no heads, that only occurs in this one case. Tails, tails, tails. So that's 1/8. The probability of getting 1 head, well, that occurs in this case, in this case, and in this case. That's 3 cases, all with probability 1/8. So the probability of getting exactly 1 head is 3/8. The probability of getting 2 heads, well, that occurs in this case, in this case, and in this case. So that's 3 cases, each with probability 1/8. So the probability of getting 2 heads is 3/8. And finally, the probability of getting all heads, that's this case, heads, 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 has probability 1/8. Notice these numbers are probabilities. They're all between 0 and 1, and they add up to 1, because 3/8 plus 3/8 is 6/8. Add 1/8, I get 7/8. Add 1 more, I get 8/8 or 1. So we've created a random variable out of this non-numeric experiment by making a number, which is the number of heads, and with these given probabilities. So now that this is a random variable, we can calculate its mean and standard deviation. The mean of a random variable, called its expected value, is computed a little differently than the ones we've calculated before. For a discrete random variable with probability function p of x, the expected value is the weighted average of the values of x, where the probabilities are the weights. For example, so we'll say that mu of this random variable, the expected value of x, is the sum of the values times the probability. Now this may look a little strange, but when the probabilities are all equal to each other, when I have n different values, all of equal probability, then that probability must be 1 over n. So the expected value then would be the sum of each of the values times its probability, but since 1 over n is the same for every term, I can pull it out of the sum. That's 1 over n times the sum of the values, or in other words, the total divided by the count. That's my usual definition for the population mean. So the population mean is always an expected value. It's just when we don't have probability assignments, when we assume they're all equal, we get the usual one. But when the values take on or occur with different probabilities, then we average this way, a weighted average where the weights are the probabilities. Let's look at an example. For the coin toss, where the random variable is the number of heads in 3 tosses, we compute the expected value of the number of heads as the product of the value times its probability added up over all the cases. That is 0 times the probability of getting 0, plus 1 times the probability of getting 1, plus 2 times the probability of getting 2, plus 3 times the probability of getting 3. Well, that's 0 times 1/8, plus 1 times 3/8, because 3/8 is the probability that we get 1 head, plus 2 times 3/8, because 3/8 is also the probability that we get 2 heads, as we showed, and plus 3 times 1/8, because the probability of getting 3 heads is 1/8. You work this out, it's 12/8. Notice that's not a probability, it's just a weighted average. So the average number of heads is 12/8, or 3/2, when I divide top and bottom by 4, but that's just 1.5. And of course that makes sense. If I toss a coin 3 times, in the long run, half the values, that is 1.5, or 1.5 is half of 3, so in the long run, half the values are heads. Here's another example. Suppose I play a gambling game where the probability of winning, that's P of W, is 0.1. Well, if the probability of winning is 0.1, then the probability of losing must be 1 minus 0.1, or 0.9. In this game, if I win, I receive $500, but if I lose, I have to pay $50. We might say that's like the cost of the game. So what would be the expected value of my winnings under this circumstances? Well, that's just the expected value of the random variable, where the value associated with winning is 500, and I multiply that by its probability, plus the probability of losing $50. I represent that as negative 50 times the probability of losing $50. Well, that's 500 times 0.1, that's the value of x times the probability, minus 50, that's negative 50, and the probability of losing 50 was 0.9, because that's the two cases. So it's 500 times 0.1 is 50, 50 times 0.9 is 45, so it's 50 minus 45, or $5. That's the expected value of my winnings. That's my mu for this case. Oops. So that means if I play the game many times, on average, with this game, I should gain $5 each time. Sometimes I'll lose 50, sometimes I'll gain 500, but in the long run, I should gain $5 each time. That means if I play the game, for example, 30 times, I should expect to win 30 times $5, which is $150 total. The table below gives the values of x along with their probabilities for a random variable. We have the value 20 occurs with probability 0.45, the value 40 occurs with probability 0.25, the probability 80 occurs with, the value 80 occurs with probability 0.15, the value 160 occurs with probability 0.1, and the value 320 occurs with probability 0.05. So your task is to first verify that this defines a valid random variable, and then compute the expected value of the random variable and compare that to just the average of the numerical values that it takes on. So please pause the video here, work this exercise. Okay, hopefully you did that. Hopefully you paused the video and worked the exercises. Let's compare answers. So first of all, we have to check that it's a random variable. Well, the values of x are discrete numbers, 20, 40, 80, 160, and 320. And if I add up their probabilities, 0.45 plus 0.25 is 0.7, plus 0.15 is 0.85, 0.95, 1. They indeed add up to 1. So each of the probabilities is between 0 and 1. They add up to 1. That defines x as a properly defined random variable. How do I compute the expected value? It's simply the total of the values times their corresponding probability. So in this case, 0.45 times 20 plus 0.25 times 40 plus 0.15 times 80 plus 0.1 times 160 plus 0.05, 5%, times 320. If you do that arithmetic carefully, you'll see that the expected value is 63. And notice that's quite a bit larger than simply averaging the numbers. If I take 20 plus 40 plus 80 plus 160 plus 320 and divide by the count 5, I get 124, much larger than 63. That's because the values don't occur with equal probability. Notice I have a higher probability of getting the smaller values, and that's what makes the expected value smaller than the simple average of the numbers. Good. So now let's move on to the variance and standard deviation of a random variable. Remember our original formula for the variance of population data. Sigma squared is computed as adding up the differences from the mean, each of those values squared, and dividing by how many values there are. If it was the sample standard deviation, I would divide by n minus 1, but here we're dealing with probability, we're dealing with populations, so we assume we have all the values. In a very similar way, for a random variable with probability function p of x, what we do is we compute the differences from the expected value, the difference from the weighted mean, squared, and instead of dividing them all by the same n, we multiply them by their probability of occurrence. Where I get the mean as the expected value of the random variable. This gives me the variance, sigma squared, and then I can always get the standard deviation by taking the square root. So let's do this calculation for our coin toss example. We had that the probability of getting a 0 was an eighth, the probability of getting 1 was 3/8, the probability of getting a 2 was also 3/8, and the probability of getting 3 heads was 1/8, and we computed that the average number, the expected value of number of heads in this experiment, was 1.5. So now we compute the variance. We take 0 minus 1.5, square that, multiply it by the probability of 0, then 1 minus the mean, 1 minus 1.5 squared times the probability of 1 heads. Then we add 2 minus the mean, minus 1.5 squared, times the probability of getting a 2, and then 3 minus the mean squared times the probability of getting 3 heads. If you do that math numerically and with care, you'll see that the variance is 0.75, adding up these individual contributions, and so the standard deviation, the square root of the variance, is 0.866. So now it's your turn. The same random variable with values 20, 40, 80, 160, and 130 and the same probability assignments. So your job is to compute the variance and the standard deviation for this random variable using the technique we just outlined. So please pause the video here and work the exercise. Okay, we're back, so hopefully you did that work. You paused the video and worked the exercises. Let's see how it should go. Remember, we found that the expected value of this random variable was 63, the mean. So now, if we, in our previous exercise, so now if we compute the variance, we take each value, subtract the mean, that's the deviation from the mean, square it, and multiply by its probability. So 20 minus the mean squared times the probability of 20, plus 40 minus the mean, it should be squared, times the probability of getting 40, plus 80 minus the mean squared times the probability of getting 80, plus 160 minus the mean squared times the probability of getting 160, and finally add 320 minus the mean times the probability of getting 320. If you do that arithmetic carefully, you get a standard deviation of a variance, the square of the standard deviation. You get a variance of 673.2, and the standard deviation, the square root of 673.2, is 25.946. And looking at that, the values range from 20 to 320, so a standard deviation of 25. Remember, even though this isn't normal, roughly all the values should be within 75, 3 of those on each side of the mean. Okay, so hopefully you found that pretty straightforward. Let's just wrap up with a reminder of what these mean and standard deviation signify for a random variable. Mu, the expected value of x, is the long-run average of the values of the random variable. When these values happen to represent financial gain or loss, the expected value is the average amount of gain or loss for each investment in the long run, as we saw with our gambling example. Sigma, the standard deviation of the random variable, represents, as it usually does, how far on the average the values differ from the mean, that is, from the expected value. The larger the standard deviation, the further the values vary from the mean. So when the values represent financial gain or loss, the standard deviation represents the risk or the uncertainty in this expected value. A large standard deviation, large variance, means there's a lot of uncertainty, a lot of risk in the investment. So hopefully you find this video helpful in getting you through section 5.1 on the Hawk system due on Monday night.